Hello everyone, a very good evening to all. My name is Akshay Kumar. Today I'll be talking about cathodoluminescence process. Let me briefly introduce cathodoluminescence for those of you who may not be familiar with this technique. So I'll start by taking a step back. Let's look at what luminescence is in general. So luminescence is a spontaneous emission of light by substance not resulting from heat. So it can be caused by chemical reactions, electrical energy, or subatomic motions, or stress on a crystal also. So there are many different type of luminescence, and it's actually around us. It's quite fascinating. So there is a chemiluminescence. So what is this? So it is luminescence that's a result of chemical reactions. There is a bioluminescence that's a result of biochemical reaction taking place uh, inside living organisms. There is a photoluminescence, that's luminescence because of the absorption of photons. And cathodoluminescence is just another type of luminescence that's caused by free electrons, and it's called cathodoluminescence because electrons were called cathode rays. Cathodoluminescence. So how is cathodoluminescence or CL generated? Let's talk about this. So when you have an electron beam that's incident on a material or any material, there's a whole host of scattering processes that can take place in this material. So when a electron beam, a high energy electron beam, can scattered to result in low energy secondary electrons, or it can scatter to result in high energy backscattered electron also. And these are the two kind of the normally detected inside scanning electron microscopy. Like we study these type of phenomena in SEM. So if the material is thin, then this high energy electron beam can also go through it. That's also the possibility, resulting in the transmitted electrons, and these are the typically measured in a TEM, a transmission electron microscopy, or STEM. You can also have other processes like generation of X-rays, which we image in EDS, or energy dispersive X-ray spectroscopy. You can also have in different Auger electrons and a lot of different kind of processes. And one of the processes can result into the emission of CL. So CL is actually just light emitted under irradiation by free electrons. It is not one thing. So its the emission takes place due to many different processes. So CL is a sort of umbrella term here for all the processes which result in the generation of light. But first of all, why is this topic is so interesting? So why do we want to image CL? Let's talk about this. So if you look at the image here, you can see a small gold nano antenna order of nanometer, which is placed in between the red circle. And if you have if you want to look at the structure optically, if you want to measure to study the nano antenna optically, then this is the result. Basically the red part, the red surfaced area is we get from the optical results, like optical diffraction spot, because obtaining optical information on nanostructures with optical microscopy is impossible. I'll not go into the details, but optical microscopy is limited into resolution, which is based upon Abbe's law. But on other side, the CL can make wonders here. So if you look on the right half of the image, in the inside, so you have an electron beam. This electron beam is like very small, of very small order, and the electron spot is shown here, and the size is something that like we can imagine relative to the size of gold nano antenna, very very small as compared to that what we are studying here. So it's much smaller, but although it's very smaller, but we get a very high resolution with such a small probe. So like we can place the electron spots on different part of the nano antenna, and we can get a very wonderful resolution here. That's why this is very important, and this is what makes it very interesting, that is spatial resolution. CL is very important. When we talk about spatial resolution, it can provide a wonderful resolution images just by playing with the electrons. So now I'm going to explain the different type of processes that happen in CL. So HCl is a very powerful technique nowadays. It's very popular also, and it has been researched a lot. So like there are two kinds of CL processes I'm mainly going to talk about here. The first kind of CL is incoherent CL. So what happens in this process, if you have an electron beam and that incident on a material, it excites electron in the material to the high energy state. So at the room temperature, the electrons, we all know it's present on the low energy in the valence band, and when they absorb energy, the electron, they are excited to the conduction band. And from here, there are a couple of different options to the electron to come back to the ground state. So it can relax directly to the conduction band, or it can also go to the intermediate states and then can go back to the valence band. So there are different type of permutation and combination possible, which result into a different type of defective states here between the valence band and the conductance band. And the difference in the energy that we are talking about here can be emitted as a photon, and that's what we image in CL. So CL signal depends upon the material properties basically. And so a material has atomic structure as well as a crystal orientation. So the CL is basically a signature of band structure in material. And incoherent cathodoluminescence basically is of two types, like intrinsic or extrinsic. So if we talk about these two type of incoherent cathodoluminescence, intrinsic, it can be caused because of the different type of vacancies, interstitial and delocalization, or the different pattern of growth, or if there is any damage of the in sample, like there are defective sites, that will result different type of CL. And on other side, the extrinsic CL is a result of basically emission because of presence of foreign dopants. So rare earth element transition metals like manganese, iron, all of this can have very strong CL signature. So even when they are present in small quantities, so these defects can result in very rich CL spectrum, very rich. So these defects can work to enhance the CL emission from some of the emission centers, and in that case they are called sensitizers, and some defect can also cut down the emission. In those cases they are called quenchers. So these are the reasons which can lead to these two types of incoherent CL. So next I'm going to talk about the CL from zircons. Very interesting that how CL is playing a very beautiful role to understand the structures So it's a mineral type zircon basically. And what you see here is a very large crystal of zircon, and this material is popular in geology because you can do like dating with it, for example. So this is in a like same image of large zircon crystal, and you can see right away it's pretty much large flat piece of rock. So there is not a lot of contrast like zonation visible here. And if you take a look on the Cl spectrum, on the other hand, you can immediately see very distinct band and zonation, which is very interesting. So this is essentially why we want to do Cl imaging for such samples, because it gives like amazing different information from what you would normally get in like SEM images. So let's go a step further and try to like quantify this little, that we have divided this image into like what if we divide, like here we have divided this image into like different zones to understand them, the different parts. So we have divided this into 7 zones here. So this is a representative spectrum. Basically on the left side, like it's we are allowing Cl to 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 enable us to explain the different type of parts and different type of contrast sections in the sample. So next I'm going to talk about that what if we pick up is we can also pick up is a particular part here, and we can get a lot of like variation, and it's not image which shows like different contrast, but like we can quantify like how this is happening, the difference between the bands, and we can see the difference between two patterns here also, and identification of different species. Here we can differentiate the species depending upon their 4f transition energies, very, and it's like they're like very sensitive. So we can talk about different zones here as well. So like if we pick like as I have discussed just a few seconds before, if we pick one of the locations like a zone, like if we pick the 6th zone and take a closer look at the spectrum, like we can actually identify the different rare elements based upon the F transitions, and it's actually a very sensitive technique, as I just mentioned before, that we can detect a few as like 10 to the power 14 atoms per centimeter cube. So again, like in this spectrum, the sharp peaks are due to the extrinsic defects, and these broad peaks that we see is a result of intrinsic defects. And the similar analysis is popular to other materials as well in geology, like for carbonates, apatites, and monazite. So it has like a broad application in the field of geology. And so this is the broad overview of incoherent Cl, and this brings me to the coherent Cl. Coherent Cl is generated any time if there is a difference in refractive index in the propagating path of the electron. If we have a material in vacuum, then the interface between the material and the vacuum would allow the generation of coherent Cl. So here is an example, like as we have discussed here, is an example of gold crystal, and when you have a high energy electron beam incident here, so when the electron passes through the material at the interface, it polarizes the material, and that polarization will lead to the interaction with the different optical modes. It can also interact with the electromagnetic wave also, and between the two optical modes. Because of this, because there is a oscillating charge that is created here, and that oscillating charge can be seen as a dipole, and this can couple with free space, and radiation can emit directly. That's the beauty of the Cl, and that's called the transition radiation. That's also the one option. So this is why the coherent CL is generated because of the difference in refractive index in the propagating path of the electron, which result into very different type of patterns or different type of interactions. So next I'm going to talk about the CL imaging system. So cathodoluminescence imaging is one of the most commonly performed in electron microscope, such as like scanning electron microscope. So we couple different type of probes along with this, and we get the CL imaging system. So on the left we have like SEM system, and here is like the electron which come from up to down in the system, and is the vacuum chamber, and we couple this with like light collection, which is collection of different mirrors, and plus the light detection part, PMT, camera spectrometer, and then accordingly we get this hardware system. And this is what a very brief description of hardware system. Let's take a look at what different parameters are important to perform seal detection. There is another picture, a very advanced picture. We can see like different type of the mirrors which are used here, and we can detect the light. And on the right side there is a detection part. So now let's talk about the CL imaging parameter. Which are the parameters which affect the CL imaging, and we should keep in mind to perform these experiments. So first of is acceleration voltage, and second is current, and third is detection parameters. So if we use a low voltage, it will not penetrate the sample that much, and as compared to if you use like high voltage, it will penetrate the more volume and will result more CL. That's what we think of. But there is also one possibility: high voltage can result into more noise. It can also sometime break the bonds, or we can get a misleaded information. So it's not always good to keep the voltage high. And the next parameter is the beam current. So like if you think of this, like is it always best to use high current? Sending in high current is good because it will generate more CL, but too high current, it may result in charging, and a higher beam current means larger spots. So there is also a risk of losing some spatial resolution. So like it's true that spatial resolution will improve, we lower the current instead of raising the current, and therefore the spot size also. But a lower current also means lower signal and more noise. So like we would need longer acquisition time to get enough signal, and that's why like we need to strike balance between there has to be balance between acceleration voltage and current. And now I want to talk about the important aspect of sample preparation for CL imaging. So these are the aspects we should keep in mind, like conductivity. So when electron beam falls on a sample, it should not it has to be mixed with some conducting metals, so that can it can if there is some charge, a possibility of charge, so that can transfer through that metal or that surface, and it also has to be compatible with high vacuum compatibility. And we also should be careful of different type of possibility when electron strikes on sample. So we should be aware of like different type of damage mechanism, knock-on damage, hitting, resonate, bond breaking, so that we don't get the misleading information, and we can perform the cathodoluminescence very well. And this leads to me the end of this cathodoluminescence. Thank you.